Hello, Math 176, Calc 2, Lesson 2. This lesson is on the technique of integration by substitution. And it is based on the chain rule from Calc 1. So let's take a look at the chain rule. Suppose we have a composite function f of g of x. And we differentiate this with respect to x. The chain rule says this is the derivative of this function capital G at g of x times g prime of x. Suppose the function capital F is the antiderivative of some function. So suppose f of u is the antiderivative of some function f of u du. So that means that the derivative of f prime of u, capital F, is little f of u. So another way of saying that is that the derivative with respect to x of f prime, of f of x, f of g of x, is equal to capital F prime, which is little f of g of x, g prime of x. So this is the antiderivative, this is the derivative of f of g of x. So the antiderivative, therefore, the antiderivative of f of g of x, g prime of x dx, is capital F evaluated at g of x plus a constant. So this is the very important formula. Let me write it down again. So it's right here. The integral of f of g of x, g prime of x dx is capital F of g of x, where capital F of u is the antiderivative of the function little f. So let's look at some examples. And I'm going to try to do examples that are in the text. So when you are studying at home, you will have seen some of these examples before, and they're a little bit easier to understand. So suppose we have the integral of x squared plus 1 squared 2x dx. So the idea is somehow to look at this function and try to get it in this form. So what we see, for example, is if we were to let g of x equal to x squared plus 1, g prime of x would be 2x. So this looks like the integral of g of x squared, g prime of x dx. Suppose we let f of u be the function u squared. Then the integral of x squared plus 1 squared 2x dx would be the integral of f of g of x, g prime of x dx. And now this is exactly in this form. So to know what the integral is, we have to find the function capital F. And what is capital F? Capital F of u is the antiderivative of little f of u du. F of u is u squared. And the antiderivative of u squared is the third u cubed plus a constant. So the integral of x squared plus 1 squared 2x dx, this is capital F of g of x. That's 1/3 g of x cubed plus a constant. What is g of x? G of x is x squared plus 1. So this is 1/3 x squared plus 1 cubed plus a constant. So this technique of substitution gives us the integral. And how can we check if this is correct? Well, you differentiate. If this is the antiderivative of this, if you differentiate this, the derivative with respect to x, of 1/3 x squared plus 1 cubed plus c is 1/3 times 3 times x squared plus 1 squared times 2x. These cancel, and we get exactly what we're supposed to get. So this is correct. Oh, that's very nice. Let's do more examples. In fact, really, we'll do a lot more examples. Here's our second example. Suppose we have the integral of 5 e to the 5x dx. So again, we can think of this as follows. If we let g of x be equal to 5x, g prime of x, or du dx, is 5. So this is the integral of e to the 5x, e to the g of x, times 5, g prime of x, dx. If we let f of u be e to the u, this is the integral of e to the g of x, that's f of g of x, f prime of x, dx. What's the antiderivative of f of u? That's the antiderivative of e to the u du. That's just e to the u plus a constant. So we get that the integral of 5 e to the 5x dx, this is capital F g of x plus a constant. What is g of x? G of x is 5x. What's capital F of u e to the u? So this is e to the 5x plus a constant. And again, we can check the derivative with respect to x of e to the 5x is 5 e to the 5x. So that's good. That works. Now, integration is not like differentiation. For differentiation, there are a small number of rules, and using those rules, you can always get the derivative. Integration has a variety of methods, If you don't know what method or what combination of methods, what sequence of methods will give you the answer, and there's a high degree of skill and artistry that goes into doing integrals. It takes a lot of practice. Let's see. Let's look at our next example. This is the integral of x times x squared plus 1 squared dx. So if you're going to make a substitution, you look for something that involves a function g of x times its derivative. So you notice that if you let g of x be equal to x squared plus 1, g prime of x would be 2x. Now, you don't have a 2x there, you just have an x. But of course, you're allowed to play with these things a little bit, so long as you don't change them in any essential way. That is, what you write down, if you have an equal sign, things are really equal. Let me write this in the opposite order, x squared plus 1 squared times x dx. I'd like to have a 2 there, but if I multiply by a half times 2, I'm multiplying by 1. I haven't changed anything. So I write a half times 2x. This is now 1/2 the integral of g of x squared, g prime of x dx. G prime of x is 2x. If I let f of u be equal to u squared, this is 1/2 f of g of x, that's g of x squared, g prime of x dx. If I let capital F of u be the antiderivative of f of little f of u, that's the integral of u squared. Oh, well, we saw that a few minutes ago. That's a third u cubed. So this is equal to 1/2 capital F of little g of x. That's 1/2 of 1/3 g of x squared plus a constant. A half times a third is a 1/6 g of x, x squared plus 1 cubed plus a constant. Let's check. So the derivative with respect to x of a 1/6 x squared plus 1 cubed is 1/6 times 3 times x squared plus 1 squared times the derivative of x squared plus 1, which is 2x. 3 times 2 is 6, cancels the 6. I get x times x squared plus 1 squared. And again, it checks. It worked. That's pretty good. Let's look at another problem. This is example 4. The integral of the square root of 2x minus 1 dx. Now, what makes this complicated is 2x minus 1. If this were the square root of u du, that's just a power of u to the 1/2. We could integrate it. So we could say, well, I wish this were just the square root of u. So let's say we make the substitution u equal 2x minus 1. If you make that substitution, then 2x is equal to u plus 1, or x is a half u plus a half. And dx du is a half, so we can say that dx is a half du. And now when we substitute, we get the integral of the square root of u, and dx is 1/2 du. So this is 1/2 the integral of u to the 1/2 du. We know how to integrate a power of a variable. You add 1 to a half, you get 3/2. This reciprocal is 2/3 u to the 3/2 plus a constant. A half times 2/3 is 1/3 times 2x minus 1 to the 3/2 plus a constant. Let's check. It's hard to integrate, but easy to check if an answer is correct. The derivative with respect to x of 1/3 2x minus 1 to the 3/2 plus a constant is 1/3. The derivative of something to the 3/2 power is 3/2. 2x minus 1 to the 3/2 minus 1, which is 1/2, times the derivative of 2x minus 1, which is 2. 2 cancels 2, 3 cancels 3. This is just the square root of 2x minus 1. So that works again. Oh, that's pretty good. Let's make it a little more complicated. Suppose we have the integral of x times the square root of 2x minus 1 dx. So we're going to use the same method or technique or trick that we did a moment ago, because I don't like this 2x minus 1 under the square root sign. Suppose I let u equal 2x minus 1, just as I did before. So if I solve for x, x is equal to u plus 1 over 2. And dx du is a half, so dx is 1/2 du. So when I substitute, I get the integral of, what is x? U plus 1 over 2 times the square root, that's the square root of u, times dx, which is 1/2 du. So 1/2 times a half, that's 1/4 times the integral of u plus 1 times the square root of u. That's u to the 3/2 plus u to the 1/2 du. Well, this is easy to integrate. This is 1/4. The integral of u to the 3/2. You add 1 to 3/2, you get 5/2. So that's 2/5 u to the 5/2. You add 1 to a half, you get 3/2, so you get 2/3 u to the 3/2 plus a constant. And then you substitute back, what is u equal to? So 2 over 20, this is 1 over 10 u, 2x minus 1 to the 5/2, plus 1/4 times 2/3, that's 1/6, 2x minus 1 to the 3/2, plus a constant. Is this correct? Well, the only way to know for sure is to check. if you take the derivative with respect to x of 1/10 2x minus 1 to the 5 halves plus 1/6 2x minus 1 to the 3 halves plus the constant, but the derivative of a constant is 0. This is 1/10 times 5 halves 2x minus 1 to the 3 halves times 2 plus 1/6 times 3 halves times 2x minus 1 to the 1 half times 2. This is equal to 5 times 2 is 10 over, this is like equal to 1/2 2x minus 1 to the 3 halves plus 1/2 2x minus 1 to the 1 half. Is that the same as that? Let's see. So let's factor out a 1/2 2x minus 1 to the 1 half. That's the square root of 2x minus 1. And then we get 2x minus 1 plus 1. The 1's cancel, the 2's cancel, and that's exactly what we get. So if you check this yourself carefully, you see, good day for us. We got the right answer again. Okay. So this is using substitution to compute some indefinite integrals. What about computing some definite integrals? So there is a very pretty formula. Well, actually, before I do that, let me just give one more simple rule about definite integrals. And this is sometimes called the power rule. And it says the following. So this is power rule. The integral of a function to the raised to the nth power times its derivative is equal to what? So if we let f of u be u to the n and u be equal to g of x, then this is f of g of x, g prime of x dx, exactly. So this is equal to capital F of g of x, where capital F of u is the antiderivative of f of u, little f of u, which is the antiderivative of u to the n, which is u to the n plus 1 over n plus 1 plus a constant. So this is equal to 1 over n plus 1, g of x to the n plus 1, plus a constant. So a lot of the examples we've seen previously are special cases of this power rule. For example, if we had the integral of x to the 5th plus 7x cubed plus 2 to the 10th power times 5x to the 4th plus 21x squared dx, If we let g of x equal to x to the fifth plus 7x cubed plus 2, then g prime of x is 5x to the fourth plus 21x squared, n is equal to 10. This is exactly 1 over 11 g of x, x to the fifth plus 7x cubed plus 2, raised to the 11th power, plus a constant. Or if we have the integral of cosine cubed x sine x dx, this is the same as the integral of cosine cubed x, put a minus sign in front and a minus sine x here. Minuses cancel. If we let g of x be equal to cosine x, g prime of x is minus sine x, n is equal to 3. This is equal to 1/4 cosine of x to the fourth power plus a constant times a minus sign. And you can check by differentiation that this is correct. Okay. Now, change of variables for definite integrals. So we have a function that we're integrating, and it somehow is of the form f of g of x, g prime of x dx, and we're integrating from a to b. So this is now a definite integral. And our formula says that this is the same as the integral of f of u du from g of a to g of b. So this is a lot simpler looking like that than that. So why is this true? Where do we get such a formula? So suppose we let capital F of u be the antiderivative of little f of u du. So then the integral from a to b, the integral, let's look at the indefinite integral. The integral of f of g of x, g prime of x dx is capital F of g of x. So the integral from a to b of f of g of x, g prime of x dx, by the first fundamental theorem of calculus, is capital F of g of b minus capital F of g of a. So that's just capital F evaluated from g of a to g of b. Capital F is the antiderivative of f of u. So this is the integral of f of u du from g of a to g of b. Right? What is this? You take the antiderivative of little f, that's capital F, and you just evaluate it at the difference of the endpoints, g of b minus g of a. So that is a little proof. And in Math 176, we like to show you the proofs, but you don't have to know them. What you have to know is how to apply them. So again, let me write down this change of variables formula. If capital F of u is the integral of little f of u du, then the integral from a to b of f of g of x, g prime of x dx, is capital F of g of b minus capital F. Well, let me write it in the form that we're using it. It's the integral from g of a to g of b of f of u du. That's the form we want. So here's the first example in the text. The integral from 0 to 1 of x times x squared plus 1 cubed dx. Let me rewrite this as the integral from 0 to 1 of x squared plus 1 cubed x dx. And if I were to let g of x equal x squared plus 1, g prime of x would be equal to 2x. I'd like to have a 2x there. So if I multiply by 2 and I divide by 2, this is a true equation. If I let f of u be equal to u cubed, so this is 1/2 the integral from 0 to 1, x squared plus 1 cubed is f of g of x, g prime of x dx. By this formula, this is 1/2 the integral of f of u du from g of 0 to g of 1. That's g of x. G of 0 is 0 squared plus 1 or 1. G of 1 is 1 squared plus 1 or 2. So this is the integral, 1/2 the integral from 1 to 2 of u cubed du. This is equal to 1/2 1/4 u to the 4th from 1 to 2, which is 1/8 2 to the 4th minus 2 oops, 2 to the 4th minus 1 to the 4th. 16 minus 1 is 15. And the answer is 15 over 8. Let's do one more. So in the book, this is example 9. The integral from 1 to 5 of x over the square root of 2x minus 1 dx. Again, I'd like to simplify that a little bit. Suppose I let u be 2x minus 1. So 2x is u plus 1x is u plus 1 over 2. Dx du is a half, so dx is a half du. When I make this substitution, when x is equal to 1, u is equal to 1. When x is equal to 5, u is equal to 9. So when I substitute, this becomes the integral as u goes from 1 to 9, x, what is x? U plus 1 over 2 times 1 over the square root of u. Wow, du. That's equal to the integral from 1 to 9, 1/2. U over the square root of u is u to the 1/2. 1 over the square root of u is u to the minus 1/2. This is equal to 1/2. When I integrate u to the 1/2, I get 2/3 u to the 3/2. When I integrate u to the minus 1/2, I get 2 u to the 1/2. Evaluated from u equal 1 to u equal 9. That's 1/2. When I plug in u equal to 9, this is 27. And when I plug u equal to 9 into this is 2 times 3. Minus what I get when I plug in u equal 1, which is 2/3 plus 2. So let's see if the arithmetic will work out. This is 1/2. 3 into 27 is 9. 9 times 2 is 18 plus 6. Minus 2/3 plus 2. 2/3 plus 2 is 8/3. So this is 1/2. 24 minus 8/3, which is 1/2. 72 over 3 minus 8 over 3. 72 minus 8 is 64. And 2 into 64 is 32. Let me just double check to make sure I didn't make too many mistakes. I'm integrating x over the square root of 2x minus 1. I let u be equal to 2x minus 1. So x is u plus 1 over 2. When I substitute, x is u plus 1 over 2 over the square root of u. Du, dx is 1/2 du. I should have a 2 there. 2 times 2 is 4. And 4 into 64 is 16 over 3. And that is the correct answer. That is the technique of substitution. I want to mention just one last thing, and then we'll be done with lesson 2. We have a function. Some functions are what are called even or odd. So a function f of x is even if f of minus x is equal to f of x. So what that really means is it's sort of symmetric around the y-axis. If you reflect it around the y-axis, you get the same function. What's an example of an even function? Well, f of x equal x squared, because f of minus x is minus x squared is x squared. What's another function? f of x equal cosine x. Because f of minus x is the cosine of minus x, which is the same as cosine of x. And if you're integrating an even function from minus a to a, these have to be the same numbers, the integral from minus a to a of f of x dx, the area here equals the area over there. So this is really just, it's enough to integrate from 0 to a and multiply by 2. So for an even function, there's this simple integration fact. There are also functions which are called odd functions. We say f of x is odd if f of x is f of minus x is equal to minus f of x. So for example, f of x equals x cubed is odd because f of minus x is minus x cubed. That's minus x cubed or minus f of x. Or f of x equal to the sine of x is odd because the sine of minus x is minus the sine of x. And it's easy to see. If you look at the graph of y equals x cubed, looks like that. If you go through the x-axis, it goes from positive to negative. If you look at the graph of f of x equal sine x, looks like that. So it's not the mirror image, it's kind of like reflected through the origin. And you can see for an odd function, if you go from minus a to plus a, the area here is equal in absolute value, but negative, opposite in sign to the area there. So the integral from minus a to a of f of x dx for any odd function is going to be 0. So these are two nice geometrical facts about even and odd functions. That is the end of lesson 2. In the text, this is section 5.5 on substitution. Your homework is to do exercises from lesson 1 and lesson 2. In the course of a normal semester, there are 28 classes. In the summer, there are roughly 14 classes. So during the regular year, every class you do 1 lesson. In the summer, every class we do 2 lessons. So we've just done lessons 1 and 2. Very good. See you soon.